All right, hey guys, how's it going? I hope everybody's doing well. I'm doing well. I hope everybody's families are safe, they're safe, and nobody has the virus. So just don't go outside. And if you're gonna go outside for work, let's say you're working in the hospitals and everything, just be safe and wear your PPE, stuff like that, your gloves and your masks. And I really appreciate everybody, and I really commend you for those of you who are working in the healthcare profession now, either as a nursing area or in the hospitals. We really appreciate it. You're doing a great job, and this class comes second to that. Healthcare is the most important thing right now in the country, and especially in New York City. So if you have a problem submitting exams, submitting assignments, like some of you did, thank you for letting me know, and it's good. I'd rather have that than you slack off at work or get stressed out and come down with an illness, especially the coronavirus. So this class comes second to that. Just so worry about the real important things first. And this class is still important, but Okay. So today we're going to be doing Chapter 8, right? So Chapter 8 is going to be about gases. We're going to learn all about the different behaviors of gases and then some equations. All these equations are very similar. If you know how to do solving for x in algebra, you will dominate this chapter. It will be pretty easy. But we have some stuff to learn before we actually do the math. Okay, so announcements. First thing first, exams. Good job overall. I know the grades are, like in my Tuesday class, I think not to compare, but Tuesday class I think the average was like a 98 or something. It was ridiculous. Great job. And then my Friday class, I think it was a little bit lower, no offense. It was like high 80s, maybe low 90s. But either way, great job, everybody. You put yourself in a really good scenario, good place to get an A in the class for most of you. And even if you don't have an A, if you have a B range, C range, also ask me if you, because this is the midpoint of the semester. Ask me how you're doing. I'll give you a range, and I'll give you if you get this grade, you'll on the exam 3 and a final, you'll get somewhere maybe a B or an A. So I'll give you like a scenario like that. So like a what if. So definitely reach out to me, email, text, Blackboard, whatever. So that's that. Office hours. I know some people are confused about office hours. So they're from every Friday 3 to 5. Once the final exam comes around, I will make more office hours. So here's how it's going to work. So I'm going to open my browser. Here's Blackboard. So if you go to course 2, I'm not sure I think you have this, I'm not sure, but it's definitely on this black panel on the left side. I have course tools. It says Blackboard Collaborate Ultra. So I click that, and it brings me to this, and I create a new session, and the session will be called Office Hours. And then you click it, and it'll probably tell you to join the room. So you can do that. And then I'll be there, and then you can start talking, and then I'll start talking. I'll probably be doing something else, so you have to get my attention by either chatting in the box or by talking, and I'll help you. So I can share with you my screen. You can share your screen to me if you have questions on different homework assignments that you're doing or something else. So that's how it's going to work. If you have a problem getting into the office hour and you're trying to, you can just call me during that time, honestly. I'm going to have my phone with me, so you can just call me. Also, for other appointments, I know maybe Friday 3 to 5 some of you aren't available from work or other reasons, such as my Tuesday class, which most of you are working full-time, or maybe not now, but those of you who are in healthcare are definitely working full-time. So if you want to schedule something that's out of office hours, feel free to message me, and we can set up either a call if it's something quick, or if you just want to chat about a concept, just to hear the explanation again. That's always a good idea. Or we can schedule a Blackboard Collaborate so you can actually see my screen and we can go over different problems together. So, or by appointment/phone call. Okay. So next announcement, spring break. So spring break is next week. So I'll pull up the calendar on the right side here. And we see that this week is there. Then we have Easter is on Sunday, and then we have spring break the week after that. So 13 through 17, that week is going to be, no assignments are going to be due. So today we're going to be doing Chapter 8. So for my Tuesday class, the Chapter 8 homework, I have to change the due dates now. But it'll be due. I'm not going to take that call. I'm working. All right. So that will be due the following Tuesday after spring break. So April 21 for my Tuesday class. And it says it on Blackboard, so don't worry. When you go to the assignment for the Chapter 8 homework. So it'll be due the 21st. For my Friday class, it'll be due the 24th on that Friday. And always at midnight. When I say the day that it's due, it's always the midnight at the end of the day. So you have time during that day to complete the homework. So once again, Tuesday class, the Chapter 8 homework will be due on the 21st. And my Friday class, the Chapter 8 homework will be due the 24th. So you have all of next week to just relax and to get your life together if you've been watching Netflix on the couch all week or the last couple weeks like I have. You'll have some time to recalibrate. So nothing will be due during that time. But I will post a Chapter 9 lecture next week during spring break. And that gives you ample time to look at it. So you'll have Chapter 9. So basically, I'm giving a lecture that week anyway. There's going to be no homework for it due that week or due the next week. It would be due the week after. But we'll get to that. I'll talk to that during the Chapter 9 lecture. Just so I have everything posted. Okay. So going forward. Chapter 8's today. Chapter 9 will be next week. Chapter 11 will be the week after. So, I'm trying to think how I'm going to do this. So Chapter 9 homework will be due, I don't know, we'll figure it out. Chapter 9 homework will probably be due this week, the week after the Chapter 8 homework. So I'm going to post a Chapter 9 lecture next week. The week after that, I'll post a Chapter 11 lecture. So the lectures will be a little bit ahead of the homework being due. And then we'll have our third exam in the beginning, probably the first week of May. May 4th through May 8th. That'll probably be the third exam, but not confirmed yet because everything's all screwed up. Then that'll be on 8, 9, and 11. Then there'll be two different lectures. One of them will be a chapter, I call it 12 through 15 medley, meaning key concepts of 12 through 15. I think 16's in there too, some biochemistry. I'm going to teach you the organic chemistry, which is important for CHE-122. So it's very, very simple organic chemistry, like different functional groups, alcohols, aldehydes, ketones, maybe some of those things you heard of in chemicals. We'll be going over that. And we'll be going over some basic biochemistry, but I might teach that through going over the mechanism of coronavirus because it's very relevant now. So I can teach, because I'm a biochemist, I can go through the biochemistry in very simple terms so you learn the biochemistry and you can apply it directly to real-world applications with the coronavirus. So that'll be interesting. I think that's Chapter 16. I'm not sure, though. I don't even care about it. I don't know the chapter numbers. There's so many different textbooks. I don't know the numbers anymore. Anyway, so we'll be doing that. That'll be the week after the third exam. So that'll be the second week of May. So I'll go to calendar. That'll be May 3rd, week of May 11th. Then review for the final will be 18 to 22. Or no. Review for the final will be that week as well. And then the final will be the week of 18 to 22. And I'll give you a lot of time for that. Okay. So final, I'll put week of 5/18 to 5/22. Just so you know that's a thing. Okay. So if you have any questions, of course, you can ask me. I don't want to repeat anything because you can just go back and listen on the recording on YouTube. Okay. Chapter 8. We're learning about gases. So a lot of these gases, so you have your solids, your liquids, and your gases. Gases are usually they're small particles, they're small compounds in comparison to liquids and solids, right? You have these long, let's say a sugar, right? You have a very long compound. You have like a basic sugar. Let's see if I can get this pen thing to work. So for a sugar, it would look like C6H12O6. Oh, this is nice. Or something like that, right? So that's a big compound. Big. I don't know why I did that. All right, big compound. But a lot of your gases are going to be small compounds like this. H2, N2, O2, F2, Cl2. Or some of the other gases that we're familiar with, CO, carbon monoxide, CO2, carbon dioxide. This is nitric, you can call nitrogen oxide. There's many names for it. And different gases like this. They're pretty small. So the idea is, when they form these compounds, a lot of them are what we call inert. So inert is an important word. Inert. That means doesn't react. So inert means it doesn't react with anything. So H2, N2, O2, all the gases that are in the air, right? So the air is mostly consisted of, I think we went over this the first day of class, 80% nitrogen, 20% oxygen, and then small traces of CO2, H2, argon even, right? The noble gases, which are located over here, right? So that was pathetic, but okay. So these elements right here are mostly what consists of gases, or mostly what gas consists of. So you have your noble gases, obviously it's in the name, and then you have different compounds that include all of these elements. And a lot of the gases are inert, they don't react. So if the gases reacted together, that would be really bad, and we would all die and suffocate. Because that means eventually there's all these billions of gas molecules in the air, they would have some kind of interaction with each other, they would bond, then they would get too heavy. And they'd get heavy to the point where they would actually fall out and degasify, or there'd be pockets of gas, and there'd be pockets in our atmosphere that don't have gas. So if we walk through and try to breathe, we would start choking. It would be a really weird environment if the gases were not inert. So they're inert. That means they don't react with anything. Now, there are these gases, I'm not going to test you specifically on these, but it's important to know these gases. So these are called diatomic gases. So I'll write that word. I clicked the button, right? Diatomic. All right. So these diatomic gases, diatomic, 2 atoms. That's exactly what it means. They are inert gases, and they're the most common gases. You have H2, N2, O2, F2, Cl2. These are diatomic gases. So it's an important thing to know that if someone says oxygen or nitrogen, to know that, oh, when it's a gas, it's a diatomic gas. So if someone says an oxygen molecule or an oxygen gas, nitrogen gas, automatically think it's N2 or O2, not just the singular element. Because an oxygen element, or oxygen atom all by itself is not good. That's a very reactive thing, right? Oxygen is located top right, periodic table, very electronegative. So in order for it to be non-reactive, so we can basically say electronegativity is equal to reactivity. If something has a high electronegativity, it's pretty reactive, right? Because it wants an electron pretty badly. So I realize I'm talking fast too. You can slow down the YouTube video. So you can go down to the settings and you can slow it down. But I'll keep talking because I'm so passionate about this, right? Anyway, so things like O2, right? If you have 2 oxygen atoms together, that cancels out the electronegativity of each one. And what that does is it makes it nonpolar, right? Or inert. Nonpolar is basically the same thing as inert, meaning it's not really going to react with anything. It has no charge differential on each side, on either atom. So these are your diatomic gases. All right, moving on. Oh, that's cool that it did that. But I'm going to leave that on there. Yeah, I'll leave that on there for now. Okay, so now this is this thing. This thing is called the kinetic molecular theory of gases. It sounds complicated. It's not. Really, there's just 5 postulates that go, and every textbook has them written differently, so they're not like a law where it's like written in the same language. It's not like the gas commandments or something like that. It's basically just a guideline of how gases behave. So let's look at each one separately. So first one, and these are going to be like, oh, no, duh, of course they make sense, right? Gases move randomly with high velocities. Duh, that makes sense. They're always moving fast, which we went over. And remember, the average speed of gases is 0.5 kilometers per second. But there's a reason why the gas molecules don't go from where I am in Hoboken to where you are somewhere in the city in a couple seconds. And the reason why is because there's billions and billions, 10 to the 20 something, even more, not more quintillions, whatever, of gas molecules. And they are eventually, the gas molecules will hit each other in air, and they'll bounce off in another direction, and they'll keep bouncing off and bouncing off. It's like a huge sea of pinball balls, in essence, just like this picture shows. They're going to be bouncing off of each other, and there's a lot more than this. All right, next one. They have very small attractive forces between each other, or any forces, even repulsive forces, between each other, between the molecules. And that ties into the inertness of gases. So that most of them are nonpolar, and they're inert, and they don't want to react with one another, because then you'd have a problem, like we said. Next, occupy a much larger volume than the volume of the molecules alone. Now, that one makes sense, too. Because if you think about it, the room you're in right now has billions and billions of gas molecules around it. Yet, you can walk right through the room effortlessly, even though the entire room is occupied by a lot of gas molecules, by billions of them. So the volume of those gas molecules, if you were to condense all of them together and squeeze them, or increase the pressure, which we'll learn about later, would be probably the size of a penny, maybe even probably a little bit bigger, maybe. So it wouldn't be that large of an actual volume that the molecules take up. But once they disperse throughout the room, it's like they're not even there. Because if you didn't learn about this, someone had to figure this out about gases, and it was only figured out in maybe the 16 or 1700s. So that means all through human history, nobody knew these gas molecules even exist. They just know, oh, we breathe and we live. They had no explanation for it. This is why. Because they're so inert, they don't react with anything. They don't react with electricity or anything like that. And they occupy such a small volume individually that there's not really many primitive ways of detecting gases. Now we have tons of ways, but primitively, a long time ago, there wasn't many ways to do that. So they occupy, and this is the reason. These postulates are the reasons. Okay, next, they are in constant motion, moving rapidly in straight lines. That ties into number one, where they move randomly with high velocities, and they're moving in straight lines. And this ties into also they're inert, right? Because if they're moving in straight lines, that means they're not reacting with anything in their way. Let's say you had a positive charged bead or a positive charged gas going through the air, and there are other positive charged molecules nearby. So what would happen? Let's see if I can draw on this. No, I'm under select. So you can draw. So if you have a positive gas going through and there's positive charges around, this gas is not going to move straight. This molecule will start to bend away from the positive charge, right? Because they're repulsive. That's not true with gases, because there are no positive charge gases that we're going to be dealing with. And they don't have charges at all. So they're inert, right? So they're going to move in constant motion and in straight lines. All right, so next. This one sounds complicated, but it's not. They have Kelvin temperatures proportionate to the average kinetic energy of the molecule. What the hell does that mean? In other words, temperature increases. I don't know why I did that. Temperature increases. Speed increases. That's literally what it means. So the Kelvin temperature is proportionate to the average kinetic energy. Kinetic means of motion. So the average speed, right? Average speed energy of the molecules. So if you have a low Kelvin temperature, let's say if you're 1 Kelvin, you're going to have very slow molecules, very slow gases. If you're at 200 million Kelvin, you're going to have really fast gases. So it's just proportionate. Okay, moving on. So these are, we'll go over these kind of quickly, and you can go back. So these are the properties of gases. So some of these variables. So these are the variables that we're going to be using today in this lecture. Pressure, volume, temperature, and amount. Right? We've seen some of these before. We've seen temperature, we've seen volume, and we've seen amount. We've dealt with moles before, right? Moles and grams. But pressure is the new one. So there's going to be equations that involve some or all of these different variables, and we're going to be able to solve for the missing one. That's what we're doing. So all of this is going to be what I like to call plug and chug, meaning let's say there's an equation with 4 variables. You're given 3 of them. Find the 4th one. There's going to be a lot of algebra. So I hope you're good at math. All right, volume. You understand what volume is. It's the amount, or it's the space that something takes up. And with gases, they take up the space of the container that they're in. So liquid, I could spill liquid on the floor, and it only takes up a certain amount of space. But with gases, I can just release gases into the atmosphere, and they take up the whole atmosphere in time. All right, next, temperature. So temperature, we know what temperature is, and we're going to measure it all the time in Kelvin. So always Kelvin in this case, right? We're always going to convert. Sometimes I might try to trick you and give you a Celsius temperature. Always convert it to Kelvin by this equation. Where am I at? All right, so Celsius plus 273 equals Kelvin. And yeah, you could be like, oh, in the textbook, it's 273.15, whatever, same thing. It's close enough. Okay. And this is important, just like I said before. When the temperature of a gas is decreased, the molecules have fewer collisions. It's just a different way of saying it. Okay, a disclaimer here. A lot of this stuff is exactly the same as things I'm repeating, but saying it in different phrasing. So, if before I said if you increase temperature, you increase speed, right? If that's the case, then if you increase the speed of the molecules, and there's a lot of them, isn't that going to increase the amount of collisions? Yeah. So let's go to this bullet point. If the temperature is increased, the molecules have more collisions. That is basically saying their speed increases. The more speed you have, the more bouncing off of other molecules you're going to have, and the more collisions. So that goes hand in hand. These are saying the same thing. So I know, like, I could be saying a lot of different things, but a lot of it is very similar, and it comes from the same entity of information, the same concepts of gases. When the temperature is decreased, right, they're going to be slow, like big and slow. They're going to bounce off of each other less frequently, therefore have fewer collisions. So that's how that works. Okay, next one, pressure. We didn't learn this one yet. Okay, so pressure is the force that something puts on you per unit area. So that's really what the definition of pressure is. I'll put it right here. So, wait. I'm still getting this. The pen has 2 buttons, and I don't know how to use them yet. All right, so pressure equals the force per area. And we're not going to use this equation in this class. It's more of a physics equation. But this is the definition, and it helps you understand it. So, pressure, let me think. So, let's say a needle, right? So you can put a needle, somebody, and a lot of you guys deal with needles in healthcare, right? I hate needles. And I hate getting shots. Well, shots are okay now. I hate getting my blood taken. Oh, it's awful. I'm like one of those people that like almost pass out. Now I'm getting better at it, but when I was little, I had to lay down because I get like squeamish. Anyway, so if it takes little effort for a needle to go into your skin, right? The reason why is because, so I'll put needle. Force is small. There's not really much of a force required. But the area that you're applying that force is in the tip of the needle. A very small, I'll put 2 arrows, a very, very small area. So let's say the force you put is 1 Newton. The area that you're applying it to is 0.0001 centimeter. Very, very small surface area that you're applying the force of the needle. If you do this math, this equals like 10,000. That's crazy. That's a big force. That's a big pressure. So you are putting pressure on. You're putting a lot of pressure into the skin. Therefore, it breaks. It exceeds the needle pressure exceeds the pressure that can be taken by the skin. Therefore, you can draw blood very easily from a small surface area. But if you try to penetrate your skin with a hammer, right, it's going to require a lot more. I'm using morbid examples, but it's going to require a lot more force. The reason why is because to do the same thing, your force has to be a lot because your area is also bigger. The head of the hammer, which is hundreds of times bigger than the head of the needle. So I'll put hammer. Yeah, so that's that. So that's what pressure is. Now, pressure, other ways, you have atmospheric pressure. So atmospheric pressure is not gravity. It's different. It is the pressure that the gas above us is putting on us. So think about it this way. Pressure is literally a force that's being pushed, right? And it's usually caused by a lot of mass that is above you. So think about it. We have thousands and thousands of kilograms of gases that are above our head. Since they're pretty spread out and they're inert and all those properties we mentioned before, the atmospheric pressure that's put on us, meaning the force put on us by the gas molecules, is not going to be that great. And our bodies are adjusted to it. That's what the normal atmospheric pressure is. It's actually 1 atm. So atm is the unit, which I'll talk about in a second. 1 atm. That's the atmospheric pressure. So that above our heads, the mass above our heads pushing down on us due to gravity, is what creates the pressure. I'll say that one more time. That's a good way to summarize it. The mass above our head of gases being pushed to the earth by gravity, that force on top of us is what creates the pressure. But we're very used to it. If you increase the pressure, let's say if you go underwater, right? And underwater, the mass of water is really, really heavy compared to gases. You can't go more than, I don't know, I never went diving before. I could barely swim. I can swim, but not well. So let's say if you go like deep diving, right? You can only go a certain point, maybe a couple hundreds of feet, before your lungs will actually start to collapse and it'll be hard for you to breathe. The reason why is all pressure, because you're going to have thousands and thousands and thousands of kilograms of water, a lot heavier than the air, that's going to be pushing down on your body. It'll actually compress your lungs. It'll make you harder for the muscles in your chest to expand, your diaphragm, to expand your lungs and to get air in, even if it's through if you have an oxygen tank. It'll actually, like, it's a force on it's a pressure on your chest that you can't physically breathe. So that's why you either need a special suit or you need to be in like a submarine. So that's an idea of pressure. But then when you come up closer to the surface of the water, it becomes a lot easier to breathe because that weight, that literal weight, the weight is taken off of your chest because you're out of the water. There's nothing above you. All right. So units, the units that that pressure is in. There's 3 that are important, 4 that the fourth one you should know about. And don't worry about PSI. That's for, like if you do, everything in America is PSI, pounds per square inch, like bicycle tires, car tires, stuff like that. We're not going to talk about that in chemistry. We mostly talk about these 2, but this one's a 3rd optional. And there's some equations with pascals. All right, so mmHg, millimeters of mercury, or torr. They are technically not the same unit, but they're very similar. It's like, I'm not going to write it down, but it's kind of like 1.001 torr is equal to an mmHg. They're very similar, basically a 1-to-1. So what this means is that millimeters of mercury. So what you can do is you can take a barometer, which measures pressure, right? And let's say you have mercury. Mercury is very responsive to pressure changes. What it does is it expands and contracts based on pressure. So at let's say a pressure you have this, if you increase the pressure, the mercury is going to get compressed by a certain amount. This difference can be measured in millimeters in a calibrated barometer. That difference is the mmHg, millimeters of mercury. So that's why they call it that. And that's the same thing as torr, which is just another unit. Then you have ATM. ATM is our SI unit standard for pressure, and this measures atmospheres. So, like I said before, when I first mentioned ATM, our atmosphere gives us 1 ATM on average. But let's say if you're in the mountains, it gives you less. If you're like in Colorado, probably 0.8 ATM, stuff like that. All right, so yeah, so I'm gonna write the conversion up here. So you have, here's the conversion, and I'm gonna give you these conversions. So 760 is the key number. mmHg equals 760. Oh no, how do I undo? I'm gonna erase. All right, so 760 torr equals 1 ATM, like that. So this is the conversion that we need to know. Okay, well that we need to, it's on the test. All right, next, so here's a barometer. That's basically what I explained before with how they get mmHg. Okay, units of pressure, here's a bunch of units of pressure. We talked about the important ones. The important ones are these: atmospheres, mmHg, and torr. Those are the important ones. Torr. Here we go. Okay. All right. Moving on. Study check. So knowing the conversion, which I'll write right here, 760 mmH. Nope, not mmg. 760 mmHg equals 1 ATM. Knowing that conversion, we're going to express this. So what is 475 mmHg expressed in ATM? So 475 mmHg. We want mmHg to cancel out, so we're going to put 1 ATM on the top divided by 760 mmHg. mmHg will cancel, and then we get whatever 475 divided by 760. I'm assuming it's probably B, probably 0.625. Okay, so next one, the pressure in a tire is 2 ATM. We're going backwards from ATM into mmHg. So we want ATM to be on the bottom this time, right? Because we want it to cancel out in the denominator. And 760 mmHg is going to be on the top. ATMs will cancel, and we will get 2 times 760, or 1520. Okay, so that shouldn't be too bad. Okay, moving on. There's the answers. Nice. All right, so now we're going to get into the laws. There are several gas laws. And, yeah, well, you can go back and you can... So I would say in your notebook, summarize them. As I go over them, just write them all down like in the same chart. I think there's a chart at the end where it summarizes them. But let's just go through it. So, Boyle's law is the inverse relationship between the pressure and volume. Okay. So, another thing before we go over these laws. There are not too many. There's probably like 5 of them. It doesn't matter. They don't matter. I'm not going to test you which law is this. I'm going to test you on probably math with the combined gas law, which is a combination of all of them. And you have to be able to use the equations rather than just memorize which ones they are. So let's go over this. So Boyle's law, inverse relationship between the pressure and volume of a gas. So let's go to a detailed thing of that. This is perfect. So this is, ignore the writing. And by the way, here's the equation. P1V1 equals P2V2. So let's look at case A versus case B, and let's see what's going on. So in case A, you have in all these cases we're going to have pistons. So what a piston is you have a cylinder with a certain volume, right? And you have gas in it. A piston is a cylindrical plate that can be put directly above in the cylinder, and it floats freely. The force that keeps the piston up is the pressure of the gases underneath it. So the pressure of the gases are actually pushing up and keeping that piston levitated. So that's what a piston is. It's kind of like, why can't you, if you fill up a plastic bag and you like choke the air off, why can't you just push down on it infinitely? It gets filled up with air and you can't push down on it enough, and if you do, it breaks. The reason why is pressure. The pressure of the air inside the bag is working against the force of your hand pushing down on the filled bag. And then eventually, if you push down hard enough, your hand's not going to break, but the weakest thing is going to break in that system, which is usually the paper bag or plastic bag. And it'll make a popping sound. And then the air will come out. So pistons are very similar, but none of this stuff's going to break. The piston's not going to break. The container's not going to break. Just the traits, pressure, volume, temperature of the insides will change. So let's take a look at this. Volume, 4 liters. Okay, arbitrary. Pressure, 1 atm. Sure, normal atmospheric temperature, normal atmospheric pressure. Then we are going to forcefully push down on the piston. What will change? The volume will physically get smaller. It'll go from 4 to 2. In that case, the pressure will have to increase. So the pressure is the amount, is another way to describe pressure, is the amount of force that the particles, in terms of gases, the amount of force that the particles are putting on the container. That's pressure. This is another way of saying it. I'll write that down. I'll write that down. So pressure equals amount of force molecules put on container. All right. That's what pressure is. All right. Oh, I don't know why I did that. All right. Here we go. Okay. So if that's the case, then we are putting pressure, we are putting force on the piston. We are decreasing the volume, which at the same time increases the pressure. And this can be described by this equation. P1V1 equals P2V2 by the inverse relationship between them. So if the volume decreases, the pressure increases, or vice versa. If I took piston B, that was my initial state, and I relaxed the piston, right? If I just took it up, the gases will have more room to move. Therefore, they will put less pressure on the outside of the container. So the pressure would decrease. They'd have more room to move, meaning their volume would increase. So you'd have this case where you have a 4-1. And if you put these in the equation, 4 times 1 equals 2 times 2. So it'll always work out that way. Okay, so I hope that makes sense. And here's some examples of that. Let's do let's look at inhalation, Boyle's law. All right. So when you inhale, and this is important now because of coronavirus, because it affects your alveolar sacs in your lungs. So when you inhale, your lungs expand. What that does is it increases the volume of your lungs, right? So let me get here. So during inhale, not inhate. Inhale, what happens is the pressure decreases and your volume increases, right? So you have gases in your lungs. the pressure of the volume of your lungs increase. The gases that are in your lungs, they have more room to move, so the pressure decreases. And what that does is, remember, I think I told my Tuesday class, not sure about my Friday class, but I talked about this thing called gradient. Everything in science moves along a gradient, usually from high to low. And that is definitely the case for pressure. So, for pressure, let's say you have 1 atm out here. Once you expand your lungs, you have 0.8 atm. Let's just per se. What will happen is the gas will naturally, with no energy, move, or the gas will have energy, but with no external energy being applied to the system, the gas will move into your lungs because it will go from a high pressure to a low pressure, and it will try to equilibrate the pressures. When those pressures are equilibrated, that's when inhalation stops. So let's say your VO2 max. The way you have a bigger VO2 max, or like maximum deep breath, is the amount your lungs expand is more. If that's the case, that means more air can be taken in, and therefore more oxygen. More air can be taken in order to equilibrate those pressures. So that's with that. And then during exhalation, what happens is the opposite. So the lung volume will decrease. Therefore, the pressure within the lungs will increase. And that pressure in the lungs will be higher than the pressure in the air. Therefore, the air would be exalted from not exhumed, that means burned. It will get forced out of the lungs. So air flows from higher pressure in the lungs to the outside, which has lower pressure. Okay, so I hope that makes sense. Let's do an example with Boyle's law. All right, so you have Freon, which was used as a refrigerant. What is the new volume of an 8-liter sample of Freon gas, initially at 550 mmHg, after its pressure is changed to 2,200 mmHg at a constant temperature in moles? Okay, important thing. Constant temperature in moles. This means that we're not changing the temperature, and we're not changing the amount of gas. Using these laws, here's a disclaimer. When we use these laws, we're going to be using, in this case, Boyle's law, because that's the only one we learned. P1V1 equals P2V2. Any variable that is not in the equation is considered constant. Such as, there's nowhere there's temperature, and nowhere there's amount or moles. So don't worry about that right now. Okay, so let's do the question. So you can pause it if you want to do it by yourself. But basically what we're going to be solving for is we're going to have our new volume. So that can be V2, right? It doesn't matter. There's different ways to do it. You can make it V1 if you want. So this is going to be V2. But equal, well, here's what we'll do. Let's make a new tab. All right, here we go. So you have, there's different ways you can do it. But the important thing is you keep the correct pressure with the correct volume. So you don't want to switch them. That's the common mistake. So what is the new volume? So new volume. Oh, it's asking for what is the new volume. So V2, we don't know. Of an 8-liter sample of Freon initially at 550. So we have V1 is 8 liters. P1 is 550 mmHg. And also after its pressure is changed to 2,200. P2 2,200. And this is mmHg. So we will solve for this. We'll do 550 times 8, right? P1 V1 equals P2 V2. So we have 2,200 times V2, which we are solving for. So if we divide 2,200, 2,200, we will get our answer. So that's exactly what they do. And they do that, and they get 2. So that's very simple. 2. Okay, good. I hope that makes sense. You can rewind or slow it down if it doesn't. Okay, we'll do another one. So in this case, we're still using Boyle's law. Let's read it. You can pause it to do it on your own. Sample of oxygen gas is a volume of 12 liters at 600 mmHg. So this is going to be our initial condition. It tells us right here. It's important to understand the language of the question. So it's asking for a sample of oxygen gas has a volume of this at that, meaning that's our initial condition. We already have our V1, which is 12 liters, and our P1, which is 600 mmHg. What is the new pressure? New pressure. Therefore, we're being asked for the new pressure if we don't have it. When the volume changes to 36, V2 equals 36 liters at a constant temperature in moles. So we can solve this again. P1 V1, P2 V2. So I'll write that up here. P1 V1 equals P2 V2. So we can do 600 times 12 equals P2, unknown, times 36. Divide by 36. Divide this whole thing by 36. And whatever this is our answer. And I don't know, I think I don't know, maybe 400? I'm not sure. Let's see. And the answer is 200. Okay. So well, we did the math right. But I was just me guessing. So that's how you do it. Okay, so you can take a look at... So the way the book does it and the way the slides do it, the explanation, they solve for the variable that you're looking for. In this case, we were looking for P2. They solve for P2 before they put numbers in. So it makes it... That's the physics way of solving equations. You never put the numbers in until the last minute. You always put in the variables so you can keep track of your variables and you don't accidentally mix them together. Because when you're dealing with numbers, you can accidentally multiply them together to create like two numbers into one, and that might confuse you because you don't know where the variables went. So if you keep the variables together, what the hell's going on? All right, yeah. So if you keep the variables as letters, it can help you, and you can solve it that way. But I'm going to do it with the numbers because these aren't too bad. Okay, so let's do this one. So for a cylinder containing helium, indicate cylinder A or B represents a new volume for the change. All right, so initial, here's the initial. When the pressure decreases, which one is it going to be? So you can pause and answer it. But basically, so here's your initial volume. Pressure decreases. That means the gases from here are going to have more room to expand. And that will be B. When the pressure increases, you're going to decrease their volume and give them less room to expand, right? Because Boyle's law is an inverse relationship between pressure and volume. So that would be A. Like that. Good. All right. This is another one. You could do this one on your own. Yeah, so you can pause and do that on your own. And the answer is 240 milliliters. Very similar to the ones we just did. Okay, another one. You can do that on your own. Very similar to what we just did. Okay. All right, next law. Charles's law. So, Charles's law is saying that if we increase the temperature, now we're dealing with temperature and volume. If we increase the temperature, we also increase the volume. And let's use pistons as our example. All right, so ignore the words. Let's look at the pistons. So this is condition A, is the first one. A, and this is B. All right, so in A, you have a temperature initially of 200 Kelvin, a volume of 1 liter. You have the piston here, and in this case, the piston is free floating. It can go up, it can go down, based on the pressure inside. So, like I said before, the variables that are not in the equations are considered constant. Pressure and moles are constant, right? Because they're not in the equation. And before, we had pressure was not a constant. Pressure and volume were changing. In this case, volume and temperature are changing. So let's take a look at it. You have a temperature of 200 Kelvin, volume of 1 liter. Okay. Heat it up. You double the temperature. You heat it up to 400. What's going to happen is these molecules are going to move faster, right? Because remember that if you increase the temperature, increase speed. Not sped, speed. Yes, it will increase the speed. So, if that's the case, these molecules are moving faster, and they're going to want more room to move in order to keep their same pressure, in order for the pressure not to change. Because they want to be at equilibrium. They don't want to change pressure. So what they're going to do is they're going to hit against the outside of the container, hit against the piston, and actually expand the piston until these molecules are quote-unquote happy, until they have a equilibrium pressure where they're happy. The temperature increase directly causes that, causes the volume to increase because of what I just said. Okay, so I hope that makes sense. Moving on. So here's Charles's law. Oh, let's go back. Let's circle the law. So the law is V1 over T1 equals V2 over T2. That's the law. And I will give these laws to you on the test. Now, you notice that it's not a multiplication, it's a division. That is because they are directly proportional. Let's take a look at this in the equation. So V1 is 1, T1 is 200. In this case, V2 is 2, T2 is 400. These numbers are equal, right? You simplify that, you get 1 over 200. So they're equal. And it's saying that if one of them goes up, the other one has to go up by the same amount, by the same multiplicity. So volume, if you increase the temperature by 2, by times 2, the volume times 2 also. So that's why they're called directly proportional. So directly. Okay, moving on. So we're not going to do that. Okay, let's just do examples. Hold on, I got to sneeze. Okay, I didn't have to sneeze. Okay, I feel like as I keep talking, I'll have to sneeze. Alright, I didn't have to sneeze. It's like you feel it coming on, but it's like a long time. Anyway, so let's do this one. A balloon has a volume of 785 milliliters at 21 Celsius. If the temperature drops to 0, what is the new volume of the balloon? Okay, first things first. Whenever you see Celsius, always convert to Kelvin immediately. So do that immediately. I would say do it right now. 21, so you don't forget. 273. So that's going to be 294. And then you have 0 is going to be 273. So 0, 273. So those are our temperatures. Okay. So let's take this. Let's go to a new page and we can do it together. All right. So our equation is V1 over T1 equals V2 over T2. All right. So our V1, so the way I do these equations is I read them, or these questions. I read them, I write down the variables as I read them, and I see what we're missing and what equation can be used to solve it. So a new balloon has a volume of 785 milliliters. 785 milliliters. At 21 Celsius. T1, 294 Kelvin, because we converted it already. If the temperature drops to 0, T2, 0. Or not 0. It would be, oh no. Nope. Okay, it would be, this is 294, this is 273 Kelvin. What is the new volume of the balloon? So we don't know V2. So we can just solve. And we know which equation we're using because we are given volume, temperature, and not a volume. Therefore, Charles's law is the easiest one to use. So in the questions on the exams, homeworks, I'm not going to tell you which equations to use. It'll be your job to write down all the variables and to know what equation works. And I'll give you all the equations, but to know, oh, this one, I have 3 out of the 4 things, I can easily solve for the 4th one. Therefore, I use it. That's the kind of logic we need to be having. So let's do this. 785 over 294 equals V2, which is unknown, over 273. So we multiply 273 times 785 over 294, and we get V2, whatever that is. Question. Some of you are thinking right now, why before my volume was in liters, now it's in milliliters? The answer is it doesn't matter, at least for right now. For these equations, it doesn't matter whether your volume is in milliliters or liters, as long as it's the same for V1 and V2. Temperature always has to be Kelvin, because let's say if we put 785 milliliters is equal to 0.785 liters. If we put that in here, it would still work and we get the same answer. But our V2 would be in liters, not milliliters. We can't do that for temperature. We can't go from Kelvin to Celsius because, or we can't make these Celsius because the multiplicity is different. So what I mean by that, 1 Celsius, 2 Celsius. To get from 1 Celsius to 2 Celsius, you multiply by 2. Those corresponding temperatures in Kelvin, 274, 275. To get from here to here, you do not multiply by 2. That is not how that works. So the multiplicity difference between different units of temperature is really important. So that's why you always, these equations are meant specifically for Kelvin, so we use Kelvin. And they won't work the other way. Okay. So I hope that makes sense. Moving on, we have our answer as 7. Did I do that right? Yeah. Okay, so 724. All right, let's do another example. This time we have room to do it here. All right, so here's what I'm going to do. I'm going to read the equation or question. I'm going to write down what we have. Sample of oxygen gas has a volume, V1, of 420 milliliters. At a temperature of 18. T1, 18, plus 273 equals 291. At what temperature in Celsius, it's asking for Celsius now, will the volume of the oxygen be 640? So we know V2, 640 milliliters. T2, unknown. Okay, so now let's do Charles's law. So V1, 420 over 291 equals V2, which is 640 over T2. So we can solve. Algebraically, this one's a little bit more difficult. We can move T2 over here. We can multiply this to there and then that down there. Keywords, if you know cross multiplying, whatever you do to take T2 by itself. So this expression would end up being T2 equals 640 times 291 divided by 420. So that would be your expression for your answer. And that, so let's do it right here. I'm going to get my calculator out. This will be 640 times 291 divided by 420. I got 443, right? But this is 443 Kelvin. Look what they did. They put 443 Celsius here as a tricky answer. The question is asking for at what temperature in Celsius. So you have to take 443 minus 273, and that equals 170 as our answer. So that would be our answer. Okay, I hope that makes sense. I hope all this stuff makes sense. Yeah, it's kind of weird to teach it without having any questions, but I want you guys to be able to repeat or to see it multiple times. All right, this is it. We did it already. Nice. All right, so let's do this little study check. You could do this on your own, but we'll go over it now. Pressure blank when V decreases at a constant temperature in mole. So pressure and volume, they're inversely proportional, right? Boyle's law. So pressure will increase when volume decreases, right? Remember the pistons? So if you push down on the pistons, you are decreasing the volume. What that does to the pressure, increases it. Now let's look at next one. When temperature decreases, so we're making it colder, less movement, the volume will decrease because you have less movement, less force against the container, everything kind of compresses. Pressure blank when the volume changes from 12 to 24, so volume is increasing, the pressure is going to decrease. Because the gas molecules, the same amount of gas molecules, same amount, constant amount, is going to have more room to move. Volume blank when temperature changes from, so temperature is going to increase, volume is also going to increase. Because this temperature change will make the gas molecules a lot faster. If they're faster, then they're gonna want to push on the container more. But since it's a piston at constant pressure, the only way to keep a constant pressure and to increase their movement is to increase the volume. So that's why it's that. Okay, good. All right, next one. I think the last one, yes, is Gay-Lussac's law. All right, so Gay-Lussac's law has to do with temperature and pressure. So before, we dealt with, so far we had P1 V1 equals P2 V2, and we had V1 over T1 equals V2 over T2. Now, the only combination we didn't do yet is temperature and pressure, right? Temperature and pressure. So this one is going to be another directly proportional relationship. It will be P1 over T1 equals P2 over T2, like that. And this piston example shows you why. So let's take piston number 1. Wait, is it the same piston as last time? It is. All right, I'll explain it anyway. So you have pressure at 1 atm, temperature at 200. Double the temperature. The pressure will, if you keep the volume this, oh, it's not the same one. So if you keep the volume the same, so let's say this piston is held in place. It's not hovering anymore. You can't move it. The volume is held constant. If that's the case, if you increase the temperature, these gas molecules are going to want to move more. Their speed is going to increase. But they cannot push on the piston in order to decompress it, in order to push it out and change the volume. So the pressure will have to increase because they'll be moving faster. They'll be putting more force on the container. So the pressure would increase. That's Gay-Lussac's law. And we can go directly to an example with it. Here we go. So I will take this example. We're getting pretty good at this now. So I will take this example. I will put it in a new tab. And we will do it. So this is Gay-Lussac's law. And I'll show you how none of these laws really matter. The next one does, the combined gas law, which combines all of these. And I'll show you a tricky way to do it. Okay, so I'm going to come back to this one after we do it. All right, so a gas has a pressure of 2 atm. P1 equals 2 atm. Same approach, right? This is, you should, if you practice this on the homework, you'll get really good at it. The same approach, just keep doing it. Reading it, writing the variables. P1 at a temperature, T1 of 18. 18 plus 273, 291 Kelvin. Always convert to Kelvin first. What is the new pressure? New pressure, unknown, since it's asking for it. When the temperature is 62. T2, 62 Celsius, plus 273. I'm too tired to do math. Too lazy. And you have 335. Okay. So now we're going to use our equation for Gay-Lussac's law. P1 over T1 equals P2 over T2. P1 is 2. T1, 291. P2 is unknown. T2, 335. Multiply T2, and you get 335 times 2 divided by 291 equals, oh, I don't know what happened there, equals P2. I like this little pad. This pad was like $35. It's really good. All right, so that's what our expression is. This one for P2. So, and yeah, so 2 times 335 divided by 291, and you get 2.3 ATM. Like that. Okay. So good. All these laws work the same. We'll do another one right now. So a gas has a pressure of 641 torr. Again, it doesn't matter which unit you use for pressure and volume, as long as it's the same on the left and right side of the equation. So P1 at a temperature, I'll write T1 over here. T1 of 128, automatically add 273 to it. 128 plus 273, and that's going to be 401. P2, so what is the temperature in Celsius if the pressure increases to 824? So P2 is 824 torr, this is Kelvin, and T2 is unknown, right? Because it's asking what is the temperature. So it's always good to look at the terminology and what they're asking for. That means you need that. That's what tells you what variable you're finding. All right, so P1, 645 divided by T1, 401, equals P2, which is 824, divided by T2. Okay, so then we're going to multiply this over here, do the cross-multiplying stuff. So our final expression would be T2 equals 824 times 401 divided by 645. And this number will give us 824 times 401 divided by 645. That's 640, I think. 640. And then, since we are being asked for what is the temperature in Celsius, if we subtract 273, we get 367 Celsius. And if I did my math right, nope. Wait, what did I do wrong? Oh, I think I typed in the calculator wrong. 824 times 401. Oh, yeah, I definitely did. 645. Yep, so I got 512. I got 512. That's going to be then 239. 239 Celsius. All right, sorry about that. Okay, good. All right, so now, if you don't understand anything we did, that's not good, but it's okay, because the combined gas law is literally what it sounds like. It combines everything that we just did. So here's a very good, this chart's amazing, because look what it tells you. It tells you the laws we just went over, these three. If you combine them all together, you get the combined gas law. So the combined, look in the numerator. Let's look at everything numerator. Numerators, P1 and V1. Numerator, V1, P1. So our numerator, by consensus, is P1, V1. That's our numerator for the combined gas law. Our denominator, the only thing in the denominator for any law is temperature. Therefore, temperature is on the bottom. So this is the combined gas law. All these three laws we just went over are the combined gas law broken down when you have constants, either temperature, pressure, or volume, with constant number of moles. The next thing we do, which is called the ideal gas law, where we will not have a constant number of moles. We will be changing that, but we'll get to that in a bit. Okay, so this is the combined gas law, and we will just do some examples with it. All right, so I will take this example, and I will bring it to, nope, I just duplicated. I will bring it to a new slide. Alright. Alright, so a gas has a volume of, so let's write down the ideal gas law, or the combined gas law. So P1 V1 over T1 equals P2 V2 over T2. Honestly, this one is really the only one you need, but minus the ideal gas law, which we didn't get to. But out of the three we just went over, if you just know this one and how to use it, you're good. And here's an example. So a gas has a volume of 675 milliliters. V1, 675 milliliters. At 35 Celsius. T1, 35 plus 273. 35 plus 273, 308. 308 Kelvin. And 646 mmHg. So P1, 646 mmHg. What is the new volume? Okay, that tells us V2 is unknown. Of the gas at negative 95 Celsius. So T2 equals negative 95 plus 273. So let's see that. Negative 95 plus 273. 178. 178 Kelvin. And a pressure of 802 equals 802 mmHg. Okay, so using this equation up here, we can solve for this. So 646, which is P1 times V1, 675 divided by 308, which is our T1, times our P2, equals our P2 times our V2, which is unknown, over 178. So you can multiply the 178 there, divide the 802 there, and you get your answer. So we'll do that here. This is V2, and you get 314. Okay, so that's how the combined gas law works. We will do another example, because I know this stuff could be difficult. We'll do one more example, and then we'll do the ideal gas law, and then partial pressure, and that's it. All right. So a sample of helium gas has a volume of 0.18 liters. All right. So V1, 0.18 liters. A pressure, P1, of 0.8 atm. Yes, I'm not using proper sig figs. I don't care. And a temperature of 29. T1 equals 29 plus 273 equals 29 plus 273. That's 302. 302 Kelvin. At what temperature? Okay, so this time we're looking for temperature. T2 is unknown. Will the helium have a volume of 90 milliliters? So this is tricky. In this case, they give you, for volume, liters, 0.18, and milliliters as 90. So you cannot use 90 here. Or if you do, you have to change this one to 180. So in other words, the volumes have to be the same unit. So what I'm going to do is I'm going to make this 0.09 liters. So then we have liters for V1 and liters for V2. That checks out. And now we have a pressure, P2, of 3.20 atm. So now we're looking for temperature. So we can do that. So I'll set up the equation. P1, 0.8 times V1, 0.18 divided by T1, 302, equals P2, 3.2 times V2, 0.09 divided by T2, which is unknown. So we can take T2, move it over here, and you can solve this however you want. Multiply that to there, divide this by here, divide this on the bottom. And your answer, you get 604 right here, 604. And then it's asking for, I think, Celsius, so you do 604 minus 273, you get 331. Okay, so hopefully this makes sense with the combined gas law. There are YouTube videos at the end It's just, honestly, practice, practice, practice. The Chapter 8 homework will be really good help. And if you're stuck, because this math stuff could be confusing, if you get stuck, call me and or call me, text me, email me, whatever. We will arrange a meeting. I promise. Because I understand that if I go through this stuff once, some of you who are more mathematically inclined might get it immediately. Some people might not get it. Some people might need to hear it 4 times so you can rewind it. So that's why I'm going through. If it seems like I'm going through kind of fast, that's why. Different skill levels. You can repeat what I'm saying by rewinding. You can slow it down, and you could also, if you need one-on-one help, if you just like don't get it, I will explain it to you in different terms if you make an appointment. So definitely do that. Okay, moving on. Ideal gas law. So in this case, all right, so far we have the combined gas law, which is your P1V1 over T1 equals P2V2 over T2. In that law, we do not need to have a specific unit for everything except for temperature. Temperature is always Kelvin. But our volume could be either milliliters or liters or something else. Our pressure could be ATM, mmHg, whatever. In this case, for the ideal gas law, that's not true. We need specific units. And the reason why is because we have a constant called R. So, for those of you who've taken high school chemistry, if you've ever heard of PIVNERT, in other words, PV equals nRT, that is the ideal gas law. That's what we're doing now. So, in this case, for this ideal gas law, we have a specific number of units. Now, on the exam, I will give you the equations. I will give you the ideal gas law. I will give you the R. So R we didn't learn yet. R is a constant. It's a number. R is 0.08206. I will give you that number as well. But what I will not give you is the units that everything else is required to be in. So, for example, pressure. I'll go over all these soon, in the next slide. Pressure has to be in ATM because this constant has a unit of ATM per Kelvin mole. It's a weird unit, but that's the constant unit it has. That means in order for the equation to work, the constant units, meaning ATM per Kelvin mole, has to cancel out with all the other variable units. So what that means is this pressure can't be in mmHg. You can't have mmHg cancel out with ATM. This one has to be in ATM. Volume has to be, this is liter ATM per Kelvin mole. That's even a more obscure unit. So I'll rewrite this in the next slide. Now, the volume has to be in liters. Has to, because our constant dictates that by the units. So I will give you this constant with its units. But it's your job to know that me giving you the constant and its units tells you that the rest of the ideal gas law equation has to be using those units. N has to be in moles. N is amount. We didn't cover this one yet in the equations, but we will now. So N is amount in moles. R is the constant. T is temperature and has to be in Kelvin as always. That didn't change. All right, so let's write this out. All right, so P. So in this case, we're going to be dealing with, there are different R constants. In the textbook, there might be a list of them. But the one we're going to use is 0.08206 liter ATM per Kelvin mole. And it's mole to the -1. So it's like divided by Kelvin mole. All right. So our pressure is going to be our pressure is going to be in ATM. Our volume is going to be in liters. Our amount is going to be in moles. And our temperature is going to be in Kelvin. So this is very important. I'll put a star next to it. That's important that you know this, what unit they're all going to be in. Okay, and the reason why this works out is because of the constant. So to drive that point home, I want to do something interesting. So if I write just unit, I'm gonna show you why this is true. I'm gonna write out PV equals nRT with just the units. I'm not even gonna write numbers or letters or anything. I will just use units. So here's what I mean: ATM times liter equals mole times, now R has this big long unit, liter ATM per Kelvin mole. Temperature is Kelvin. You can see what's happening. All right, so I just wrote out the equation in terms of the units. Watch this. Mole cancels out with mole. Kelvin cancels out with Kelvin. Liter with liter. ATM with ATM. Boom. Draw a smiley face. Yeah. There we go. I wouldn't be good at using this pad for art, but make it a snowman. Alright, kind of a saggy snowman. Okay, I can get carried away with this. Alright, we're done. Give him a little tie. Alright, good. So, that is how this works. Now, let's just jump into examples. Now, this slide shows you the different ideal gas. Oh, this is just the constant. Yeah. Okay, now, under these conditions, the reason why it's called an ideal gas law is because it makes a lot of assumptions about how gases behave. And there's a word for these assumptions, and it's called ideal, making it an ideal gas. No real gas is ideal, but we just make a bunch of assumptions, such as we assume there's no friction, we assume there's no resistance of any kind, or we assume these like other physical properties aren't there. Most of them are kind of negligible. So when we have an ideal gas, another important thing to know, more for Chem 2, is that 1 mole of an ideal gas with the ideal gas law has a volume of 22.4 liters at this thing we call STP, right? So STP is important. This means a standard condition for gases. So standard temperature pressure. So STP. So standard temperature, 273 Kelvin. Pressure, 1 atm. So this is telling you that all the time, 1 mole is going to have a volume of 22.4 liters at this STP. And you can actually figure this out using the ideal gas law. So PV equals nRT, you could do pressure times your volume equals the number of moles. Let's say we're doing a standard for 1 mole of gas. Our ideal gas constant is 0.08206, and our temperature is 273. If you solve for this, you just basically solve this. If you do, I'm gonna do it right now. 0.08206 times 273, you get 22.402 or whatever, right? 22.4. This is telling you, this is just a standard condition that it's like a good number to know, right? That let's say your Chem 2 professor asks you, quick, how many liters is 1 mole of gas at STP at 273 Kelvin and 1 atm? You're going to be impressive and be like, boom, 22.4 liters. So and it's used a lot in chemistry. So that's a good thing to know. All right. So let's do. There's also other units of the ideal gas constant. So the one we're going to use is, like I said, it's in liter atm per mole Kelvin, or per Kelvin mole. There's another one, 62.4. That's in liter, and instead of atm, mmHg per mole Kelvin. Not used as much, but let's just focus on one at a time. All right, let's do an example. Here we go. So, we have the laughing gas. What is the pressure in atmospheres of 0.35 moles? All right, so N equals 0.35 moles of N2 at 22 Celsius, so 22 plus 273 equals 295 Kelvin in a 5-liter container. 5.00. All right, so we're looking for what is the pressure, unknown, right? And we know R. R is always the same. All right, so let's put this in the equation. P, unknown. V, 5, equals nRT, 0.35. And R is 0.08206 T. T is 295. So if we solve, divide by 5, like that, pressure equals, what are we going to get? We get 1.7 ATM. So pressure equals 1.70 ATM. So in this case, all we're doing is we have 5 variables, 1, 2, 3, 4, 5, or this is a constant. We really have 4 variables, these 4. And we're just solving for the missing one, which is pressure. So hopefully that makes sense. Now, something I didn't do before is I want to go back to this one. And I want to solve it using the combined gas law just to show you that it's possible. So I'm going to erase all this. Hopefully you're following. I know it's a longer lecture. I'm hungry. It won't take too much longer. Probably like 15 more minutes. Okay. So let's solve this using the combined gas law, right? So P1 V1 over T1 equals P2 V2 over T2. All right. So we have a pressure, P1 of 645, temperature of 128 plus 273. We don't know we don't know the temperature number 2, but we do know the pressure 2 is 824 torr, like that. All right. All right. So now we have all this stuff. We have pressure. We have 645. Our volume. Volume. We don't have volume in the equation. Oh wait, look. V and N remain constant. All right. If they remain constant, we can just say they're any constant. Let's say 1. T1 is 128 plus 273 is 401. 401. Yeah. P2, 824. V2. Oh, wait. What is V2? There's nothing in the equation. Oh, wait. V and N remain constant. Okay, it was 1 before. It's still going to be 1 in the second case. T2, unknown. So you see how, because we kept the other one, we're using the combined gas law. But if we simplify it based on what the equation is literally telling us, that V is constant, we can get rid of V completely. The 1's cancel. It turns into Gay-Lussac's law. And we're back at square one where we can solve it easily. So that's just to show you that using the combined gas law for all of these, except for when you're dealing with moles, you have to use ideal gas law. So moles, wherever you see moles or amount, you use ideal gas law. Whenever you don't see moles, you always use the combined gas law. Or if it's really simple and you can use Boyle, I'll give you all of them so you have your options. Okay, going back. Did that one, good. All right, so here is what we need to know for our units. So just to summarize what I showed you before. For this constant which we're using this one. We're going to be using these units. Pressure, ATM, volume is in liters, amount, moles, temperature, Kelvin, like I went over. Okay, the last thing is partial pressures. All right, so partial pressures are so easy, a caveman can do it, right? Basically, just to tell you what's going on, here's the equation. Dalton's laws of partial pressure. If you have different atmospheric pressures of different types of gases, let's say you have nitrogen gas is 0.8, oxygen gas is 0.2. The total atmospheric pressure is 1. Why? You add them together. So if you add the pressure of different gases, you get the total pressure of the container of the system. That's basically it. So here's examples. If you have different mixtures of gases, right? So you have 1 mole of, and it works in a molar ratio if they're ideal. So there's a lot of math with ideal gases, and like it can go deeper than this, but we're only going to go so deep. So if these gases are ideal gases, right, at STP, the molar ratio, and I'm not going to test you on this per se. So the molar ratio, the molar amount is equal to their pressure. So what I mean by that is, and look at this case, if you have 0.4 moles of O2 and 0.6 moles of helium, that's 1 mole of gas total. That 1 mole of gas, since it's at STP, remember, 1 mole of gas at STP has a volume of 22.4. If that's the case, it's STP pressure, meaning standard pressure, 1 atm. Doesn't matter what your mixture is. It just matters that the final molar amount. So here's what we're getting at. If you have 1 mole of nitrogen, 1 mole of, let's say a different, I can't talk. So if you have 3 gases that equal 1 mole, 2 gases that equal 1 mole, 1 gas that equals 1 mole, 200 gases that all their amounts add up to 1 mole of gas, at STP, your pressure will still be 1 atm. The reason why is because these gas molecules are so small that it doesn't matter if the gas is argon or hydrogen. Even though argon is so much bigger than hydrogen, the small nature of these gases, infinitesimally small molecules, that the size difference between argon and hydrogen is negligible, to the point where 0.2 moles of argon, which weighs a lot more than hydrogen, is the same pressure as hydrogen if you put them in a container. That's how small these gases are. So that's just a concept thing. Okay, but math-wise, all right, so you have a scuba tank. So here's the kind of questions I'm going to give you. So let's say you have, the work's right here, or some of it is. All right, so a scuba tank contains O2 with a pressure of 0.45 atm of oxygen. Helium is at 855 mmHg. What is the total pressure in mmHg of the tank? So the partial pressures, we add them up. So P total equals the pressure of the oxygen plus the pressure of the helium. But we cannot simply add 0.45 to 855. Why? Because they're in different units. You have ATM, mmHg. So you need to convert. You can convert everything to ATM, or you can convert everything to mmHg. It doesn't matter as long as in the end they're the same unit. So here they converted the ATM to mmHg. You got 342. So they're simply going to add 342, which is the oxygen, plus the 855, which is the helium. That's 1,100 something. That's 1,200-ish with sig figs, and you get this, 1.2 times 10 to the third. Why is this x here? I'll get rid of it. Oh, no. Okay, good enough. All right. So let's do this one. So for a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 atm. This is telling you the total pressure is 8 atm. So PT equals 8. If the oxygen has a partial pressure of 1,280, so PO2 equals 1280 mmHg, what is the partial pressure of helium? So we don't know the partial pressure of helium. Before, we had to just simply add up both the temperatures, or both the pressures. In this case, we can't do that. We have the total, we have one component, so we need to add the other component, which we don't know, and solve for that. So we can convert this 8 atm, we'll do 8 times 760, So times 760, that'll give us 6,080 mmHg. So I just did a very quick conversion. All right, so now let's do the math over here. Our P total is 6,080 equals 1,280, which is our P of oxygen, plus P of helium. So we're going to just simply subtract 1,280 minus 1,280 and 1,280. We get 4,800 mmHg. And it's asking for, yeah, an mmHg. So we got C. Good. So 2 ways I could ask this question. I can give you the total pressure and ask for one of the components, or I can give you both components and ask you for the total, which is easier. But I can ask you both of those things. And there will be some converting in the middle. Here is a, oh, yeah, here's a, there we go, good. All right, blood glucose, we don't have to cover that, doesn't matter. Okay, so that's basically it. I know I've been talking for a long time. Let me see this for a second. This will get confusing. I could put a video about that. Anyway, so I talked for enough. Here's videos. So if you want to cover the gas laws again, here they are. Here's the ideal gas law, of a YouTube video on it, and practice problems. Because I know, so the best thing is practice. So let's see where this link brings us. I forgot, this was a while ago I made this. Let's see. Oh yeah, there's a bunch of them. Good. So here's a bunch of them, and you can actually do them in your notebook, and you can write the answer here and check it. So this is something that it's not going to be, you know what, how about this? I'll make it extra credit. Yeah. So if you're listening, and you only get the extra credit opportunity if you listen to this part. So if you listen the whole way through, and you send me this completed, like just screenshots of it, I'll give you extra credit. Account for a homework assignment. How about that? Okay, good. So it's like a hidden Easter egg in the class. All right. So that's it. Yeah. So stay safe again. So, yeah. Good job. Good job for everybody. Bear with me on this online stuff. I know it could be difficult. Some of you are freaking out. Some of you are like discouraged a little bit. But let's get through this together. I know this is a tough time. I know chemistry at BMCC is probably not the thing you're focused on the most. And I understand that. But let's bear with each other. Let's help each other through this. So I know you guys talk to each other and are friends. So that's great. If you have problems with the lab, let me know. And remember, some of you have been stressing out about the lab. You told me, so that's why I'm saying this. I have the say in the matter at the end. I make your final grade. So be nice to me. No, I'm kidding. But be nice to me. Not to saying that everybody wasn't. That was just like a joke. But good job. Keep it up. And stay safe. All right. So see ya next week. And happy spring break, of course.